So in the last video, I defined the following two spaces, Cm and Zn m comma z mod 2. These two spaces are topological spaces. There are naturally defined topologies on them. We have the boundary map from the space Cm to Zn m comma z mod 2. So I'll just write Zn instead of Zn m comma z mod 2. So this map sends the region U to the boundary U, and this is a 2 to 1 map. This is 2 to 1 because if sigma is boundary U, then sigma is also boundary of M minus U, since M is a closed manifold, and these are the only two possibilities. We have the following theorem by Marquez and Neves. The space Cm is contractible, and the boundary map is a double cover. Therefore, the space Zn is homotopy equivalent to Rp infinity, and the cohomology ring of Zn with Z mod 2 coefficients is the polynomial ring Z mod 2 lambda, where lambda is in H1 Zn comma Z mod 2. And we recall that the space Zn is the space of generalized hypersurfaces which are boundaries. And on this space, we have the area functional. The idea of the Amgren fits min-max theory. It's to construct closed minimal hypersurfaces, which are precisely the critical points of the area functional using a min-max method. Applied to the area functional defined on this infinite dimensional space Zn. So more precisely, we have the following theorem, which follows from the combined works of Amgren, Fitts, and Sensheimer. It says that given any closed Riemannian manifold, Mn plus 1, n plus 1 greater than or equal to 3, there exists at least one closed minimal hypersurface in M. So this theorem says the existence of at least one one closed minimal hypersurface in M. But as I said earlier, the cohomology ring of Zn with Z mod 2 coefficients is the polynomial ring Z mod 2 lambda, where lambda is in the first cohomology class. So in particular, Hi, the ith cohomology class of Zn with Z mod 2 coefficient is non-zero for all I. Therefore, from the finite dimensional Morse theorem, one expects that the area function has infinitely many critical points, that is, there exist infinitely many closed minimal hypersurfaces in M. This was conjectured by Yao. We have the following theorem which proves this conjecture. It follows from the combined works of Marcus Neves and Song. It says that if the ambient dimension n plus 1 is between 3 and 7, then any closed Riemannian manifold Mn plus 1 contains infinitely many closed minimal hypersurfaces. So in lower dimensions, when the ambient dimension is between 3 and 7, any closed Riemannian manifold contains infinitely many closed minimal hypersurfaces. And for generic metrics, we have stronger results. For instance, the density theorem by I.D. Marcus Neves. The equidistribution theorem by Marcus Neves Song. Morse index lower bound by Marcus Neves. Multiplicity 1 by Zhou, and many others. So all these theorems tell us that in a closed Riemannian manifold, closed minimal hypersurfaces exist in abundance. And given these theorems regarding the abundant existence of closed minimal hypersurfaces, it is natural to ask for a given C greater than 0, whether there exist multiple CCMC hypersurfaces in M. So Zhou and Zhu developed a min-max theory for the AC functional, which was later developed by Zhou. More precisely, we have the following theorem by Zhou and Zhu. Let Mn plus 1 be a closed Riemannian manifold with the ambient dimension n plus 1 is between 3 and 7, given any c greater than 0, there exists a closed, almost embedded hypersurface in M with constant mean curvature C. So given any c greater than 0, there exists a closed almost embedded hypersurface in M, which is CCMC. And here almost embedded means the following. So almost embedded means that all the self-intersections are one-sided tangential intersections. So near a point of self-intersection, we have a following picture. We have the following picture. Let's say this is the point of self-intersection, and if we loop inside a ball around this point, we'll have two shapes touching. And a remark here is that we have the following remark. So in this theorem, n plus 1 is between 3 and 7. If we have n plus 1 is greater than or equal to 8, then we still have the existence of a closed CCMC hypersurface in M, but it can have the CMC hypersurface can have a singular set of Hausdorff dimension at most n minus 7. Okay, so this theorem guarantees the existence of at least one closed CCMC hypersurface in M for any C, and then building on the works of Zhou and Zhu, I prove the following theorem. Let mn plus 1 be a closed Riemannian manifold with n plus 1 greater than or equal to 3. Then the number of closed CCMC hypersurfaces in M is at least a constant gamma times c to the power minus 1 by n plus 1. So n plus 1 is the ambient dimension and gamma is a constant which does not depend on c, but gamma depends on the ambient metric. So in particular, this number tends to infinity as c tends to 0 plus. So the number of closed CCMC hypersurfaces in M tends to infinity as c tends to 0 plus. And to prove this theorem, we need the properties of the volume spectrum. So I'll briefly talk about the volume spectrum. So as I mentioned earlier, the cohomology ring of Zn with Z mod 2 coefficient is the polynomial ring Z mod 2 lambda. Lambda is in H1, Zn Z mod 2. A continuous map phi from X to Zn is called a P sweep out if phi pullback lambda to the power P is non-zero in HP X comma Z mod 2. We define omega P as follows. So this is equal to sup area of phi x. So small x is in the domain of capital Phi. And then we take in over all phi. So in is taken over all capital Phi such that phi is a P sweep out. And from this definition of omega P, we have that omega 1 less than or equal to omega 2 less than or equal to so on. We have omega P is less than or equal to omega P plus 1. We have the following theorem regarding the growth estimate of omega P. So this theorem by Gromov, Booth, Marcus Neves tells us that there exist constants C1, C2 greater than 0 depending on the ambient metric such that C1 into P to the power 1 by n plus 1 is less than or equal to omega P, and omega P is less than or equal to C2 times P to the power 1 by n plus 1 for all P. This theorem tells us that omega P grows as roughly P to the power 1 by n plus 1. So we use the properties of this volume spectrum omega P to prove this theorem. So let us call this theorem 1. Theorem 1 follows from following theorem 2, which was proved in the same paper. Suppose k is a natural number such that omega k is strictly less than omega k plus 1. C greater than 0 such that C times volume of M is less than omega k plus 1 minus omega k. Then the conclusion is that there exists omega in Cm such that boundary omega is CCMC with optimal regularity, and we have the following estimate for AC omega. So omega k less than AC omega less than omega k plus W. So W is a one parameter width. It is defined as follows. So let us consider S to be the set of all lambda from 0, 1 to Cm. Lambda is continuous such that lambda 0 is the empty set and lambda 1 is the entire manifold M. Then W is the following min max number. So we take sup area of boundary lambda t. T is in 0, 1. And then we take inf over all lambda in S. So W is the min max number associated to this family S, and this is what this W is. So this theorem 2 says that whenever we have a gap, whenever we have a jump in the volume spectrum, that is omega k strictly less than omega k plus 1, and C is small enough such that C times volume M is less than the difference, then we have a CCMC hypersurface with certain estimate on AC omega. And we use this theorem 2 together with some other properties of volume spectrum to prove theorem 1.